So I just want to check your thinking on this. Not all of the cases will there be an answer that is specific and precise. Some of them are kind of subjective based on experiences. So please don't look for, well, what's the right answer in all of them? No, instead, think about probability, think about what it means, and just kind of check your thinking about probability in the first one, number A. What's the probability you reach into a bag? There's 3 red, 2 blue, 4 black gumballs, and you're going to pull out a blue gumball. So this bag has 3, 4, 5, 6, 7, 8, 9 gumballs. So the total number of outcomes is 9. Of those, the favorable ones are the blue ones, and there's 2 blue ones. And so we would say the probability of reaching into a bag and pulling out a blue gumball is 2/9. Now, what does it mean to say the probability is 2/9? It means if I was to do this experiment over and over and over and over again, a bazillion times, and every time I reach into the bag and pull out a gumball of any color, I recorded the result. And I did this for the rest of my life. And just before I died, I looked back at all the results and I counted up how many there were and how many of them were blue. What I would find is that 2/9 of the results would be blue gumballs. That is, I could rearrange things into groups of 9 such that every group of 9 had 2 blue. Group of 9, 2 blue. Group of 9, 2 blue. Group of 9, 2 blue. Rearranging the actual results into these groups of 9, I could put 2 blue in each group of 9 in the long run if I did this a bazillion times. But hey, if I only did this experiment 9 times, I might get 0 blue gumballs. I mean, you could reach into this bag 9 times and get red, 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 black, 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 red, black, and never get a blue. But if I kept doing it a bazillion times, then 2/9 of the results will be blue. How about snow falling in July in Arizona? That's kind of subjective because I'm going to guess that a lot of people are like, July in Arizona? 0% chance. Which brings up an important notion when it comes to probability. Probabilities range on a scale from 0, the thing's impossible to happen. On the other end of the scale is a 1, certain to happen. 0%, 100%. Probabilities will always fall between 0 and 1. And so you might think about a 0% chance here, but if you do, you might be thinking about Arizona as in the Maricopa County, the Phoenix metro area, or even the Sonoran Desert part of Arizona. You may not be thinking about, say, Flagstaff, Arizona. Because I've been to Flagstaff in July, and there's been snow up on the peaks at Snow Bowl. And so I might say, based on my experiences, that while unlikely, that there is a small probability, a small chance, that if I was to look back over hundreds of years in history, how many times did snow fall in Arizona in July? Well, if you count Flagstaff in the mountains, maybe a few times, so maybe not 0. So again, no right answer here, just thinking about things. Likewise here, what about July in New Zealand? You might think July in New Zealand. New Zealand is in the southern hemisphere. July in the southern hemisphere is winter. New Zealand has some mountains. Maybe it's winter in New Zealand in July. Maybe it's a higher probability there could be some snow falling. And so you come up with some subjective thing. Or maybe you actually Googled it and found some more information. The point is though to just have you think about probability in a context like this. How about flipping a coin twice and getting different results? Hey, when you flip a coin twice, here's what could happen. You could get a heads the first time and a heads the second time. You could get heads the first time, tails the second time. You could get tails the first time, heads the second time. And you could get tails the first time, tails the second time. Those are the 4 and only 4 things that can happen when you flip a coin twice. Our task is to find the probability of getting different results. Well, probability is this thing about favorable outcomes, favorable, different results. There's 2 ways you can get different results. Out of or divided by, or as a ratio to, the total number of outcomes. There's 4 things that can happen when you flip 2 coins. So the probability is 2/4 simplifying to 1/2. That is to say, if you flip a coin twice, and you do it a bazillion times, half the time you'll get two different results, and half the time you'll get the same result, like heads, heads, or tails, tails. How about rolling a die and getting a prime number? Well, when you roll a die, there's 6 things that can happen. So there's a total number of outcomes of 6. You can get a 1, 2, 3, 4, 5, or 6 on a standard 6-sided die. Now, favorable in this come would be prime number. Well, the prime numbers are 2. A prime number is a number that's divisible only by 1 and itself. So you can do 2 divided by 1, you can do 2 divided by 2, that's it. So 2 is prime. 3 is prime, it's only divisible by 1 in itself. 4 is not prime because 4 is divisible by 2 and 4 and 1. 5 is prime. 6 is not prime because it's divisible by 2, it's divisible by 3, divisible by 6 and 1. 1 is not prime, even though 1 is only divisible by 1 and itself is 1, and so mathematicians have left off of the definition of prime the number 1. So there's only 3 prime numbers. So 3 favorable outcomes out of 6 total possible outcomes. We say 3/6. We can simplify to 1/2. We would say that if you roll a die a bazillion times and record the results, half of the time you'll see prime numbers and half of the time you won't. F is very subjective. Going to a store and finding that they don't have your size in the t-shirt you like best. You might feel like, oh yeah, that happens to me. It's like a 99% chance that I'm not going to get what I want. I don't know. I'll let you just think about that one. But the idea is, if you go to a store looking for a t-shirt 100,000 times, then what number of times do you not get what you want? And that's kind of how we think about probability. The probability that a student in your mathematics class is wearing sneakers. Pretend you're a teacher now. Put your teacher hat on, and you have a class, a mathematics class, and on any given day, what's the probability that you're going to see a kid wearing sneakers? I bet it's pretty high. You might even say here that the probability is 1 or 100%. That a typical American classroom, you're probably going to see a kid wearing sneakers. Now maybe you're going to come up with some, well, but what about the day where we're barefoot day at school or something? I don't know. Okay, so maybe it's not 1, but it's going to be pretty high, pretty close to 1. How about rolling 2 dice and getting doubles? So I wanted you to see, when you roll 2 dice, notice there's red and there's green, so you can see the difference. When you roll 2 dice, there's 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. There's 6 by 6, there's 36 different things that can happen. So the total number of things is 36. Favorable in this case is getting doubles. Well, notice doubles. There's 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So there's 6 favorable outcomes, doubles. There's 6 different kinds of doubles. So the probability of rolling 2 dice and getting doubles is 6/36, which simplifies to 1/6. That is, if you were to roll 2 dice, a green one and a red one, over and over and over and over again, a bazillion times, and write down what you got each time, that if you look back and organize that data, you would find that 1/6 of the results are going to be doubles. I'm going to skip I for now because this was supposed to be a short video.